We're going to talk about some other problems that come up from time to time. And one of them that I certainly thought about was rooftop units and the various problems they create. And I always, I like to blame our mechanical engineering friends for these problems. But then we have a lot to be thankful for our mechanical engineering friends, our HVAC friends, because they're always the last ones to finish the job, aren't they? I don't know why that is, but they're always last, and so it takes a little pressure off the rest of us because their plans are never done. On the other hand, you can never, ever get the information out of them for your structural design. It's always late. So that's why we do have a lot of problems associated with rooftop units. And I say to my mechanical engineering friends, boy, that's tough engineering. They open a catalog, right? And they pick some unit. That's really tough. How come it takes you 3 months to do it? But I don't know. It's true, isn't it? One of the things associated with rooftop units certainly is vibration. Comes up from time to time where some unit vibrates too much. And the solutions certainly are, one is to modify the stiffness of the supporting steel. The old rule of thumb is that supporting beams or joists should have a natural frequency that's either 50% greater or 50% less than the operating frequency of the unit. And if you do that, then the steel's not going to vibrate. And of course, the problem is just in design, what I said, you can't find out what the natural frequency is until it's almost too late. But that's how you certainly can solve it. Another way, of course, is to provide isolators under the unit so that it dampens out the vibration. So prevention, design the support steel properly, provide isolators. And I think if you do the same kind of work and are dealing with the same type of equipment on many jobs, then you get to know and you kind of know what to do. Here's the other two sets of equations in the whole lecture. And it's just to get the member frequency. This just comes out of textbook. For a concentrated load at midspan, the natural frequency is 188 over the square root of the deflection. And for uniform load, it's 213 over the square root of the deflection. And this is unlike most things we deal with in vibration. These are in cycles per minute, not cycles per second. So you got to remember that. But those are kind of handy equations. I should have written this slide, well, in cycles per second, when you talk to your clients, I don't know if you say cycles per second. If you want to sound smart, what do you say? Hertz, right? Because it's the same, but you just sound more dignified, I guess. Okay, one of the big ones is rooftop units in the wrong location. What do? I say, number one, move the unit to the proper location. That doesn't happen, does it? They just won't do it. They just say, hey, it's now the structural guy's problem, so what do you have to do? You have to reinforce the members. And if there's steel beams, certainly you can use cover plates. You might add a new beam or a new member, slip it in there. And if joists, you can add beams. We'll talk about that. Add joists or reinforce the joists, which is not a pretty sight. This particular slide reminds me of one of my partners a number of years ago took the SE exam in Illinois. And there was a question on the exam about a rooftop unit, and it was supported by these two beams. And here's the unit weight, and do these beams need reinforcing, and if so, reinforce them. This guy, very bright guy, he's actually very big in the precast industry. And Roger looked at it, and sure, the beams needed reinforcing, and he looked and he thought, boy, the best way to do this is for me to design another beam and slide it in there and take the load. Well, whoever wrote the exam was looking for, do you know all the provisions for cover plates and welding, and so he failed. And yet his solution was probably the best solution. So he actually appealed and won the appeal on the exam, that his solution was the good solution and probably the cheapest. But don't try that. Maybe that was the old days. Joist reinforcement is a tough thing. I mentioned earlier that I am in the process, I think I mentioned this, of writing a technical digest for SJI on joist reinforcement. I have several things in this lecture on joist reinforcement, but I'll go into much greater detail when we finish the design guide, which I would say will be done by the end of the year. So you can look through that for the Steel Joist Institute website. But as far as joist reinforcement, of course, the most common thing is if you have a load that is not at a panel point, you know the top chord of the joist it can't take any concentrated extra load. In the old days, the H-Series joists were designed for an extra 300-pound concentrated load that could be put anywhere. The K-Series joists are on the money. They aren't designed for any extra. So if you have a load that comes in between, the first thing I think about doing, certainly depending on where it is between joists, is I might add a upside-down channel so I don't screw up the deck ribs to transfer the load over to the joist. And then you always have to add some sort of angle to take the concentrated load down to a panel point. And this detail, I think you know, appears now on almost every erection drawing that the steel joist people put out. They'll have this as a standard detail that says, if you don't put the concentrated load over a panel point, you have to do this. And we put it on our details too, and you probably do as well. It happens so frequently. I might add that there's some very, very nice new provisions in the AISC 2005 specification on the design of single angles. We used to have some really complicated stuff there, but the 2005 spec has a procedure that allows you to use an equivalent slenderness ratio and go right to the column tables, and it's very nice. So look for that in the 2005 spec. You might consider adding a beam. Here's a joist girder. Here's a joist coming in, and it needed reinforcing. So in this case, this was a job we designed. We stuck in this beam. Now the tough part is getting the beam in place, but also the darn beam seat. Because the joist, let's say that was a K-Series joist, the seat depth is what, 2.5 inches, isn't it? So in order to facilitate things, you need to make a beam seat that's just 2.5 inches, and in effect, we make it just 2 inches deep, so there's a chance of shoving it under there and then using a half-inch shim or something to get it into place. But this creates a little bit of a structural problem, doesn't it? Because you don't have much left for shear at that point, and you notice the stiffener going back. That's so that we don't overstress the web as well, and you have to take the bending here as well. So it's a simple design procedure, but you better remember to do it. What I have found is that it makes a big difference now that we are using all 50 yield steel. We get a better shear strength out of the web. And usually I have to pick a beam that might have a little thicker web than I would have normally picked. But other than that, it's not rocket science, as they say. But it's a nice way and a cheap way to solve the problem. How do you prevent? Well, again, we aren't going to prevent rooftop units from being in the wrong place, but what can we do to help solve the problem when it happens? And I've listed 4 things here. One is to what I call design flexible headers, and use KCS-Series joists, and I'll talk about those. Use what I call zoning, or it used to be, and I don't think we do this much anymore. Maybe you do, but I haven't seen it. Is provide extra joists. You know, I say, hey, provide 2 extra joists so that if you have a heavier unit, you can slide those into place. Now no one wants to pay for the two joists. You know, it costs $500 or something out of 10 million. So they'd rather have us screw around reinforcing joists later. Double frame. There's all kinds. I show this one. I used to use a frame like this where here the unit's sitting up here. Here's the top chord of the joist, these two. And some angles here, and then little angles or shoes that are like this, so you set them down on the joist. And you can do this. Now here I show a top chord panel point, top chord panel point. The problem that you and I have when we're designing something, we don't know where the top chord panel points are. We don't know where they're physically in the field. So if you use this, yeah, you might get lucky. Most, well, don't make a note on this, but most K-series joists, if they are, let's say, more than 20 inches deep, the panel points will be 24 inches apart, because that's the maximum the joist people can use without adding the bending into the top chord. So most of them will be 24, but you don't know for sure. So, but this frame works fine. You may have to reinforce if it doesn't land at a panel point. In recent years, I've used a double frame as I've shown here. Again, the unit sits here. Here's a joist. Here's a joist. And now what I do is I take an angle that I make the distance from this point to that point maybe 30 inches. And I design that angle so that it can span 30 inches. So if the joist top chord panel point is here, this has enough guts to span over to the panel point. I don't have to worry about where they are then. I can just set it down and it always works. So I kind of like that, and I think it probably doesn't cost much more than the other type. So you might give that some thought. The solution with KCS-Series joists, I think all of you probably know what a KCS-Series is by now. It's been out, I don't know, what, 10 years? But it's a special joist that you can specify. It falls under SJI. It has a constant moment capacity along its whole length, so it's like a beam, and it has a constant shear capacity. So unlike a K-series joist, which is designed for the shear that's present at the web location, plus a minimum of 25% of the end reaction, the constant shear capacity joist, it's tabulated. It has that capacity no matter where you put a concentrated load. It's designed so it can handle stress reversal too. A tension diagonal might become a compression diagonal, but it has the same capacity. So it's a nice joist to use if you don't know in the beginning exactly where a load's going to be, because it has a constant shear capacity. All of the diagonals are designed for stress reversal, except the end diagonal, which is 100% tension only. Okay. Except if you would specify uplift, then it would be designed for whatever uplift you have. So again, though, even with these, if the loads don't land at a panel point, you need that reinforcing. But it's a nice joist. This is what I call rooftop zone or rooftop zoning. Here's a beam, or a joist girder, doesn't matter. And here are some KCS joists, a bunch of them. And I got this from a friend of mine who, well, his name's Tom Wallace. I'll give him a plug on national TV here. Tom used to design all the Walmarts all over the country. And just like us, they would never know where the mechanical unit's going to go. They would tell him the bay generally. And he didn't know the loads or where they're going to go. And so he said, right, we use this system. And the first job they ever did with it, they used almost exactly like this. And guess where they put the rooftop unit? Over here. So all for naught. What he did tell me was they wanted it there. They realized it ahead of time. This was up. They unbolted it, unwelded it, and turned it 180 degrees, and they were fine. But you can't win. But see, you can put it anywhere here. The KCS-Series, if you're here, doesn't matter. And if you design enough fat here, you're fine. Remember that rooftop units don't have uniform density. Okay, they're always heavier on one end than the other. I, like other young engineers that were here when I was a young engineer, I used to get very particular. I would look at the rooftop unit, find the center of gravity, find the reactions at the 4 points so I could design my support beams properly. Those days are gone for me. Take the weight of the rooftop unit, divide it by 2, and it'll work. Okay, and use those same reactions everywhere. Saves you a lot of engineering time, and it doesn't cost any money. Don't forget that the weight of the curb and support frame are probably not included when they give you the weight of the unit. Some more comments now on joists. I put this picture in for a very, very good reason. Here's our joist. Here's a little HSS column and a beam sitting on top of the column. And you should all be going, oh my God, when you see that. Why should you be saying that? Because it's an unstable structure. More than likely, it's an unstable structure. You have to have a stiffener or stiffeners over here, or a joist extension or something to stabilize that column and beam. This beam will, think of the axial load as being up here. All of a sudden you have a column now that has a little thin web going up. You don't have the same L over R, okay? The other thing, and I've been mentioning this when I do some lectures on the 2005 spec, is that we often as engineers forget the basic assumptions involved in the equations we use. The beam equations that you use in the specification assume that you have a torsional restraint at the end of the beam. Don't ever forget that. There is no torsional restraint at the end of this beam. So that's important. Here's some cute pictures on joist reinforcement now. Here the plumber, he missed over here, so he went over here, and I think the next picture shows it better. This one, it cut most of the top cord, got down to this point, and I showed this the first time, and Larry Kloiber was sitting there. And I said, well, he didn't go all the way through the cord. And Larry said, yeah, it's probably because he probably ran out of drill, that they didn't go all the way through. But obviously that joist needs to be reinforced. This is not a good picture. Can you see it okay? This joist in the tension cord has a big old hump in it. That's more than likely our erector friend. He probably dropped the joist. And then, screw it, I'll put it back up, and then somebody, maybe they won't even notice it, So, and the fact that it's a tension cord, it's not so bad. But it would need to be fixed, certainly. Okay, adding joists, just a few comments on adding joists or reinforcing joists. I think it's most cost effective to add a joist to the problem for the load if time permits. Often though it's a crisis situation, and by the time you can get a joist out of the joist company to put it in place, it's too long. Maybe you can get a beam faster. So that's my next favorite thing to do is make one of those beams with the special joist seats and get that to the job site. Get it from one of the two friendly fabricators that are in the audience here. You may have to reinforce the joist or joists that are there, and I urge you to seek assistance from the joist manufacturer. They have some nice standard details, and they can give you some help. They're like anybody else, though. If they're really, really busy, they'll kind of blow you off. And they'll say, you know, I can't get to it right away, or, you know, it's going to be weeks. They're like you and I. So you may have to do it yourself. And we've mentioned how to prevent the problem. Use the KCS. I use the word here, over-design for mechanical equipment and collateral loads. Nothing wrong with a little over-design, folks, especially if you have the job already. I once heard a talk from an architect years ago, and I'll never forget what he said about the structure. He said, you know, I want the structural engineers to take skimpy, take everything you can out of that structure. Just to the point where the building's about ready to fall down. Because he says, nobody will know. But if I screw up and I don't have the HVAC system working right, and the people are hot or cold, they're going to complain. But they don't complain if they don't know if the building's about to fall down. And he said, and the other thing is, I take that extra money and I can put it into really lush carpeting. And people will remember, oh boy, that was a nice hotel. The HVAC system worked great. Lush carpeting. But the building's about ready to go, you know. But we don't do that, do we? We try not to. We do our best. Remember, just another thing that comes up are sprinkler mains, you know, the 8-inch main. Make sure it gets hung from more than one joist. Otherwise, it'll overstress it for sure, unless you've designed it that way. Okay, reinforcing. Some methods of reinforcing. One way is what I call load distribution. We'll talk about that. We've mentioned adding new joists, and I'll also mention reinforcing existing joists. Here's what I call load distribution to joists. Let's say that I have a concentrated load that falls right here. Now, if I put a little header across here, I could transfer that load to those two joists. Maybe it even falls right under one, and it would go to that joist. Now, well, from the way it's drawn here, about 3/4 of the load goes there and about 1/4 goes over there. If you had a little header. What I call redistribution is, if you design this spreader beam with enough stiffness, you can transfer this load to, well, theoretically, any number of joists, depending on the stiffness of this beam versus the stiffness of the joist. Okay? So if you go and you check and you say, oh my God, this concentrated load's going to overstress this joist by 10–15%, that's not that much. Okay? So you can say, this solution's going to work. I can design a beam, and I can actually design like a truss interior here to spread it too if I don't have the headroom. Okay? And it goes back to simple beams on elastic foundations theory as to how to do that. Or you can just put it in a computer model. Okay? So I urge you to think of that first as a way of handling the reinforcement, or not having to reinforce. Now, if you're going to add joists or beams to a facility, probably the biggest problem would be existing interference. If it's a some sort of facility where there's lots of piping, gas, mechanical piping, electrical, it may be that the cost of moving all that junk which is what we structural engineers call it, the cost of moving that in order to slide in a new joist or a beam is prohibitive. Then you can't use that solution. So the first thing to find out is what is the existing interference? What's there? Okay? The second thing I think about if I'm going to add a joist is the camber on the joist. You don't want to order a new joist from the joist manufacturer that has camber in it. You want no camber, because the facility you're reinforcing, the camber's gone. So the last thing you want is a joist with a big hump in the middle that you can't stuff into the supports. Okay? So you can order a joist with no camber. If you don't do that, you're going to get a joist with camber. They all camber them. It says it's optional in the K-Series spec, but I don't know of a single joist manufacturer that does not provide camber. So think about the camber. And then the end seats. Remember I said on the beam you might consider making that end seat only 2 inches so the erector has room to shove it into place, so you then shim it. Same thing if you order a special joist for reinforcing. Ask for a 2-inch deep seat. They can give you a 2-inch deep seat. They'll find a way. Okay? So you think about that. And then don't forget that this joist that you're putting in needs lateral support. When you design a joist or specify a joist on a plan, the joist is designed with the assumption there is a lateral support every 36 inches along the length of the top chord. And that's normally there by the deck and the deck welds or deck screws or deck pins, whatever you're using. So if you add one now, you got to make sure that you have adequate lateral support for it. And it's not a good idea, you know, to put it in and then shoot nails up vertically, because they'll probably penetrate your roof membrane. So don't do that. This drives my joist friends nuts, but I like to do it because I like to drive people nuts every now and then. I will actually have specified a joist with no end seat. And this way you see if there's no interference or very little interference, the joist really is only that long. So now the erector can build a scaffolding or something. He can put it up in the air, and then we put on the seat. And it goes in easier. And this seat is just a couple of angles that get welded to the top chord, and they have to go back to the main panel point. So this moment, you see, here's a vertical load. That moment is designed into that seat and taken out, you know, by reactions here and there.